Okay.
Thanks, Warren.
Sarah has a book.
So I can push them out. Thank you very much.
Sorry about that. I don't know what's going on there.
You can sit behind you.
So, where's the number?
You can see this is possible.
Okay. How do I get it?
Yeah, usually you guys are wow.
As the meeting starts, because we're still changing.
Most the past, but it's just fine.
If you're presenting, do you want me to do next?
Yeah.
Yeah, that's fine. As long as it's straightforward, like the arrow keys. I can do arrow keys.
Animations.
Okay. And what do I do in this?
Just next again.
Okay. Okay.
So we'll do the instructions.
Okay. That's not
Yeah, I've done this before. Just left, right, left, next to previous, and
there we go.
yeah, wrong one. And I may have to. It normally. Okay, I think you're set, doesn't? Is it? No, I'm not sure what's going on now. Maybe think of the back.
Should I push the escape button while we still have it?
Yes. I mean,
I can just do.
yeah, let's not go back to working.
Thank you, everyone. Sorry for the late start. So welcome today to the EDU tutorial on DNS privacy. My name is Sarah Dickinson. I'm very glad to see so many faces here today. So I'll move forward onto the overview of what we'll talk about today. So the tutorial is basically split up into 3 sections. The first section is going to be a background of why are we talking about DNS privacy as an issue and how did this arise? And to kick that off, Daniel Kahn-Gilmore has kindly agreed to give a few slides to set this in the context of the bigger picture of internet privacy. After that, we'll move on to talk about the huge amount of work that's been done over the last 3 or 4 years in this area, a lot of it through the IETF, a lot of it through the DPRIVE working group. And then finally, I'll talk about the current status of implementations, deployment, and the tools that are available today. So thank you. So without further ado, I'll hand over.
I'm going to have to switch.
Yeah.
So I want to talk just a little bit to set the frame for why DNS privacy matters. More generally, it matters sort of, there's a bigger picture. Why does privacy on the internet itself matter? Just to try to motivate it so that we're thinking about this stuff sort of on the same page, you can, looks like it doesn't want to do the full screen thing.
Hold on.
Is it a one-page PDF? That's fine. I can just. There we are. All right. So So the concern here is that there's a sort of an issue of possibility of a centralized surveillance state acting as a form of social control. Now, you might be concerned about governmental control. You might be concerned about criminal control, blackmail, a range of other things. But basically, whoever controls the network, if the network is transparent about what's going on, has potentially a lot more power over the citizens. So the people who use the network. So this is a plan for the Panopticon, which is a prison that's designed so that a warden sitting in the central tower of the prison can effectively see everybody in all of the cells around the outside. And so that allows one or a very small amount of people, the guards in this case, to have control over a very large population. I find that troubling, and I'd like to make sure that the network where the smarts are at the edges doesn't make it so that the center actually has control over those smarts at the edges. So the next. So the DNS, when we think about what goes on in the DNS, we're often thinking about sort of that it's basically like little bits of metadata, like what host names are you looking up? And that's associational host data. So a request comes from you for a particular name. Those names potentially mean things. And I want to just point out that like associational surveillance is actually probably the most sophisticated form of surveillance that we have. If you're thinking about global surveillance, it feels creepy to think of somebody knowing what you're saying, but actually the things that machines can learn at scale are significantly more powerful these days than just content analysis. And so this associational stuff, this is a slide from a leaked slide from the NSA. They're only one of the groups who are doing like intense associational surveillance. But the kinds of associational surveillance they can do is mapping particular people to particular groups. So you can imagine with the DNS, the sorts of mappings that could go on, did you visit Alcoholics Anonymous? That tells somebody something. So whoever controls the network has an opportunity to know, if they're just watching what traffic goes on, what sorts of people have connected to what sorts of groups. So the DNS is part of that. So you can do the next slide, Sarah. So it's also not just host names, right? The DNS has, we think of it as most commonly, it's just we're going to look up an address from a name, but there's lots of other stuff that can be stored in the DNS. And if you look around what's going on at the IETF, there are a bunch of other opportunities to use the DNS that are not just host names. They're not as widely used, of course, as the address lookups that we're all familiar with. But in fact, there's a bunch of other stuff that's coming down the pike. There's old stuff like MX records, which will actually leak information about what domain you're emailing to. And then there's things like OpenPGP key, where you might actually end up sending the name of whoever you're contacting directly to DNS. Or not the name, but the individual email account, which is a significantly larger privacy leak. So there's a bunch of other stuff that could go on in the DNS, and people want to use the DNS for that. And so we need to make sure that DNS queries aren't as obviously subject to associational surveillance. And so just to sort of reinforce why I think the social control issue is a thing here. So this is a study that was done, I think this year, at the beginning of this year, where they basically took a bunch of people and they asked them their opinion on some topics that were fairly contentious. And then they asked them their opinion about the sentence, is it like basically, is centralized surveillance okay? And it turns out that this is sort of along the lines of if you're not worried about it, if you've got nothing to hide, you've got nothing to worry about, right? There's a lot of people who have that sort of instinctive response. And it turns out the people who say, if you're not, if I've got nothing to hide, I'm not worried about surveillance. Surveillance is justified to keep society safe. The people who say that, when it comes to things where they are in the minority, where they feel like they are more in conflict, they're actually less likely to speak up. So this is actually an ecosystem problem where the fact that we have all of this additional leakage means that people are less likely to dissent and our society is less likely to be able to evolve. So these are different groups of people who have different opinions about the legitimacy of surveillance. And the graph here shows friendly, neutral, and hostile. So if you think you're saying something into a hostile environment and you think surveillance is okay, you're actually less likely to speak up at all. So there's a chilling factor of having the centralized surveillance. So it's not just about, are you individually concerned about being spied on? It's about what can society do how does society change? How does the behavior change as a result of having this? So we want to make protocols that encourage people to feel that they are protected, so that they actually can communicate with people even in an environment where they might otherwise feel like it's a hostile environment. And I want to point out that DNS is one little piece of these leakages, right? So this is a boat here. DNS is leaking in the middle of the boat, but there's leaks coming from the TLS layer, the server name indication in TLS leaks. There's leaks from the traffic size of different kinds of packets that you send, timing patterns. There's probably lots of other leaks that we don't know about. And a lot of times in the IETF, we're working in these little silos. And I've heard in multiple situations, people say, oh, well, we don't have to worry about that leakage because it's just as bad as this other leakage that's happening somewhere else. Well, in a leaky boat scenario, you actually need to fix all the leaks. You can't just say, I'm not going to fix my leak because this other leak over here is leaking also, right? We want the boat to stay afloat. So the motivation here is to try to make sure that we can actually get, I mean, there's a lot of work ahead of us. We actually, these are theoretical concerns, and some of these, like the question marks there, are real question marks. Like these are, there's ongoing academic research about what kind of information can be determined from things like timing patterns. And we don't have all the answers, but we know that if we don't fix the things that we know how to fix, we're not going to get to all of them. So that's just the motivation for why we care about DNS privacy. It's not going to solve all the problems, but it's a step in that direction. So give it back to Sarah for.
Thank you.
Well done.
Okay, thank you very much. So I hope that's given you a flavor for some of the context of what we'll talk about today. So what I'd first like to do is, before we dive right deep into what's been happening in DNS world, is talk a little bit about what's been happening at the IETF level in general in terms of privacy. Now, of course, the Snowden revelations were a big thing, and it got popular awareness about mass surveillance out there. A lot of people sort of tend to think that kind of caught the IETF napping, but what I want to illustrate here is that really isn't true. The IETF was very actively involved in all sorts of privacy work well before that. There were numerous workshops, and quite importantly, in March 2011, work was started on a draft that was to guide protocol developers on how to add privacy considerations into their drafts in a very similar manner as to the way security considerations are quite naturally put in drafts. So the folks behind that started back in 2011, and they were right on the verge of getting it published as an RFC when Edward Snowden revealed his data to the world. So you kind of got a feel for these guys a little bit, getting their thunder stolen there. But what the IETF did is it came back swinging. It very quickly reacted with a very important document, which is RFC 7258. And this declares clearly that pervasive monitoring is an attack. I'll talk about that a little more in a moment. The work at the IETF level has continued, though. There are several other RFCs in this area. There are many drafts in progress. So I just want to illustrate that there is a lot of work going on at the leadership level in the IETF with regards to privacy. I just wanted to pull out just a couple of statements from RFC 2558 in terms of clarifying that the IETF's position on this is that pervasive monitoring is an attack on internet users and organizations. And the declared aim in future protocol developments is to mitigate the effects of monitoring through protocol design. So doing it at the lowest level, not necessarily operationally, but making sure protocol design takes this into account. So to move on to see where this intersected with DNS. So if you think back in time a little bit, first of all, I'd like to time travel you back to 1987. So pick your DeLorean, your TARDIS, your phone booth, time machine of choice, and go back to 1987. So there was a lot of bad hair, a lot of good music, and the DNS was being standardized at that time. And to put it in context, at that time, it was a building block in the internet. And the main goals behind the design of the infrastructure of the DNS were availability, redundancy, and also speed. So those are the things that foremost in the people who are developing the protocol. In privacy terms, the DNS is described as an enabler. It's a system that you use to get to other services. So you want to get to a web page, you go via the DNS. You want to email somebody, you go via the DNS. So that's where it sits. Now, it was still true of the standards in 2003 that the standard transports for DNS were UDP and TCP. And even last year, over 99% of the traffic going up to the route went over UDP, and importantly, this is clear text. So all your DNS queries are going clear text over the internet. So this meant this was fair game for somebody like the NSA with their more cowbell tool. It really wasn't a tricky job for them to monitor DNS traffic because of the way it moves over the internet. There was a very small amount of TCP around, but it was really only used for corner cases. There was also at this time, and for much of the sort of 25-year time period here that I'm spanning, a perception that the DNS is public, right? I mean, anybody can query these records, anybody can get to them. They don't contain personal or sensitive information, so we really don't need to worry about encrypting this or protecting it in any way. It's the DNS. And that was out there for a long time. So you have to bear those things in mind when you look at the design of the DNS and be a bit forgiving. So this is the basics of how the DNS works. You're on some client machine. You want to resolve a name. You send the full name up to the recursive server that you're using. Now, what the DNS does is if it doesn't have that name in cache, it sends the entire name up to a root server to get a delegation for, in this case, .org. Then it sends the entire query to the .org authoritative server, and so on down the chain until it gets to the one that can provide the answer. Now, with hindsight and your privacy hat on, you look at this and go, oh, that infamous bad idea fairy was around when they thought of this, right? Because those two queries are leaking information. Who at the root needs to know the full question that the client asked? They don't need to in order to resolve it. But this was how the DNS was designed originally. Something else interesting happened just about this time frame as well, 2013. And that was the standardization of a mechanism called EDNS0. Now, this was a really nice idea and something the DNS really needed. It enabled embedding information inside a DNS query that was flexible. It could contain capability options. It could allow clients and servers to negotiate things like path MTUs. It was great. The DNS needed it. As a side effect, though, what this did is it enabled certain organizations to take advantage of this to embed user data directly inside those DNS queries. But the way this was positioned at the time was that it was all for the greater good. So, for example, one of the mechanisms here was ISPs saying, we want to offer you filtering, parental filtering, protect your kids, or even more sophisticated filtering. And we can do this at our recursors if we know who's making those queries. Similarly, CDNs argued that if we know where you are located geographically, we can divert you to your nearest server and you will get great streaming and your cat videos will never buffer again. Isn't that wonderful? Aren't we doing you a great customer service? So this all sounds great and people sign up for it. What they don't realize is what this means in practice. So the way the user identification worked is that your ISP would give you a router, and very often that router would add in to the DNS queries as they came out of your home network information about you. That might be a MAC address. In some cases, it was observed that it was usernames or user IDs, something unique. And that meant they could do their filtering at the recursive, but it also meant that anybody who was passively monitoring that link could immediately correlate all those queries with the activities of individuals behind that router. So that could allow not only for identification of individuals, but tracking of individuals as well. In a very similar manner, the way the client subnet worked was that there was an implementation in the recursive that said, well, we know who sent us this query, pick up their subnet and send that up to the authoritative so it can figure out their geolocation. But again, this is leaking information to anybody passively monitoring that link up to the authoritative, again creating correlations within the data with the activity of users or groups of users. So what this really means is, even when you're sat at home, you're behind a NAT and you think you've got anonymity, you don't necessarily. And even though you're behind a recursor and you think you've got anonymity, you don't necessarily. And both of these were done originally with non-standard options. Some of them are now coming through the standards process, but there really wasn't anything to stop organizations doing this because people were happy to sign up to the services, which sounded great. And as DKG alluded to, the kind of queries you do reveal quite a lot about you on both of these legs. So I don't know about me, but I'm at home. Before I came here, I was looking up what conference I was going to, what hotel I was staying at, what flights I was taking. So this revealed an awful lot about me, including how distracted I can get when I'm trying to put a big slide deck together and what sites I go wandering off to. But this is all information they can correlate back to me. So I hope at this point I've got your spidey senses tingling with the idea that there's all sorts of stuff going on in the DNS that you don't necessarily know about as an end user, even if you're quite technically aware. To take this another step further, so we've looked at the kind of leakages you get on DNS queries that are in flight. This is thinking about them at rest. So you have a recursive resolve that you're using. So you have to start considering who are the people who have authorized access to the data there, to what's being logged about all the queries coming in. What third parties are they sharing it with? What legal commitments do they have to gather data on users? Equally, what are the risks of unauthorized access to that data? How solid is the security? Could there be breaches? And also, those concerns will change as you move around different recursors. So as you're at home, as you're at work, as you're in a coffee shop, as you're in a hotel. And these are things that people aren't necessarily aware of. Equally, those concerns extend up to the authoritatives, because as you can see, information can make it up to that level about the activity of individuals. So those are the sort of salient points about DNS data leakage. There are an awful lot of complications. I want to just touch on one here, which is something which particularly lately has become more active, and that's DNS filtering. So this is happening at country level and at ISP level, organizational level, and it's activities whereby people running recursors will have a blacklist of sites they don't want people to get to, and they will actually tell DNS lies in order to block access to those sites. Again, this is trying to be done for the greater good, keep you away from websites infected with malware, etc., although accidentally some other sites get blocked every now and again that you might want to get to, like Google. This has happened by accident. But the thing to think about is, if you are using a recursor that engages in this kind of behavior with these blacklists, how likely do you think they are to track users who trigger their blocking due to trying to access one of these blacklisted sites, even if you do it by accident? So this table tries to summarize the hotspots in terms of DNS data leakage, in terms of what's happening on the wire and at rest, and I'll come back to this later and show you where we are in terms of tackling this. So that's a picture in classic DNS as you know it. I want to spend just a little bit of time talking about something which is called DNS service discovery. So this happens within local networks, and the mechanisms used can be regular DNS constrained to that local network, or it can be multicast DNS. What this does is essentially the procedure whereby a device can advertise some services that it is willing to make public, and other devices can discover those services and use them. And this is really cool because it means you can do stuff like file sharing, photo sharing, all sorts of stuff directly over the network. And that's nice. And most of the services that utilize this are secure. The problem comes in advertising those services. Now I can see a whole bunch of Macs here, and I know that if you simply just open Finder and look in your sidebar, you can probably see a whole load of devices advertised, and I bet a whole bunch of them have names or identifiers in them. And very typically, the kind of thing you might see is something like this. Stuart?
I was going to add one pedantic point. You said this is on the local network, but it's not. It's on the global network. Sitting here at the IETF, if you tap the AirPrint button on your phone, it'll do a query for ipp.tcp.meeting.ietf.org,
Right.
which will go across the Pacific to Virginia or wherever the authoritative server is for IETF.org.
Yeah, I was talking just about the this service advertisement is typically constrained to the local network.
Well, you're in the example you're giving, which is .local, it's local multicast.
Yes, yeah.
What I was saying is when you do it over unicast, it's going over the public internet in the clear, unencrypted.
Yeah.
Every time you tap the AirPrint button on your phone and print a document on the terminal room printer here, even though you're printing it on a printer down the hallway, you're sending a query to the US and back to ask for the address of that printer.
Right.
I mean, I'm assuming the authoritative server for IETF.org is not
Isn't in
here,
this hotel.
so it's somewhere else.
Yeah. Thank you. So in terms of advertising what you're doing here and leaking information, the problem comes with the way this information is advertised and the amount of detail it contains. So for example, you might quite easily see this kind of information advertised from an individual user. And you think, well, okay, so what? They want to share this stuff. They're willing to make it public. But think about what you've learned about Alice just from this information. If you're in a very small room and say there are only a handful of females and only one has their laptop open, then suddenly you've got a really good idea of who Alice actually is. You also know that she's got 2 devices, and you know she's willing to share photos, and that she uses a chat application that supports presence. So not only do you know a bit about her, but what you've got is a fingerprint here. So you can see this fingerprint as it moves around networks, and that means you've got user tracking capabilities. And this goes beyond tracking the user. It can go deep dive into exposing information about, for example, when you advertise these services, you also often advertise attributes about them. So for example, which ports they use, which priorities they use, lots of details. And intelligent attackers, it has been shown, can actually use this to determine things like which software version you are running. And therefore that means they might be able to detect known exploits in unpatched software. Similarly, they can actually dive right down to specific devices if they have enough information. So again, this is leakage of personal information that non-technical users are probably very unaware of, and even technical users might not understand the full gravity of. Okay, so what I wanted to do quickly was just say, okay, so back then, if you were savvy to DNS privacy being a problem, what were your choices at the time? There were a couple of things available. DNS Curve was around for a little while. DNS Crypt was developed and is still around. There are a number of implementations. So, and in fact, OpenDNS offer that as a mechanism when you use their resolvers. What I do want to spell out, though, is that the real motivation behind these mechanisms was authentication of the information exchange between clients and servers. So it was about anti-spoofing and anti-DOSing. And the privacy benefits largely came as a side effect because crypto was used to achieve that. These weren't first and foremost privacy mechanisms to protect users. Also, although these were documented, neither actually made it through the standards process. Other things that people were doing, some people chose to run local resolvers on their machines, and the main aim here was to bypass those intermediate recursors so you weren't exposing your data to them. It doesn't solve the whole problem because you're then exposing your client address directly to the authoritatives, but some people felt this was a better choice than using an intermediate recursor. Also, what came out around this time was a tool called DNS Trigger. Now, again, the motivation for this was to enable DNSSEC on an end user computer, and the privacy aspects were a byproduct. But what it did was it used as a last-ditched attempt DNS over TLS on port 443. But what this did mean is there was an implementation of encrypted DNS out in the wild that some users were able to monopolize and use for their own ends to do private DNS, even at this early stage. So, having talked about the historical context for this, I wanted to move on and talk about what's been happening in the recent years. So one of the main places this work has happened is the Deprive Working Group. And this was created in 2014 in the wake of the Snowden revelations and the desire by the IETF to mitigate monitoring through protocol design. Now, this had no small task before it. You're talking about taking the DNS, which has been a base rock of the internet for 30-some years and worked in largely the same way for all those 30-some years. And what you have to magically do is sprinkle it with a layer of privacy with minimal impact and try not to disrupt the internet while you do it. So where do you start? Well, this was a big problem, and what the working group decided in its initial charter was to focus solely on the stub to recursive step of this. And there were various reasons for this. Two I'll summarize are, one is that that stub to recursive stage leaks the most information. So if you can tackle that, you're going a long way towards helping end users. Secondly, the recursive to authoritative stage is quite challenging when you come to think about how you're going to do authentication of connections in that environment. And the reason is this: if you're an end user, your relationship with recursive servers is one to a few. You have the one you use at home, at work, when you're out and about. But generally, you either have a relationship with that recursive resolver, or you make a conscious choice to use it by going through a captive portal or joining a network, whatever. Whereas if you're a recursive server, your job is to talk to all and any authoritative servers that you need to in order to resolve a name that you have been asked for. And many of those you may never, ever have talked to before. So that makes authenticating the one to many unknowns difficult. So think of this a little bit like your phone contacts compared to your Twitter followers. Who do you know best? So the first thing that the working group did is it decided to enumerate the problem space, and it produced RFC 7626. Now, this is a highly recommended read. It basically goes through the kind of situations that I talked about in the first part of the discussion here today, but in much more detail, and it also goes through other cases of leakage. So that's really worth looking at to understand the details of what's going on. One really key thing that this document does, though, is it rebuts the alleged public nature of the DNS. And the distinction it makes is that, yes, the data in the DNS might be public, but an individual DNS transaction is not and should not be public. So to use the same example as earlier, and this is actually directly taken from this RFC, the website for Alcoholics Anonymous is public. The A record for that is public. The fact that you as an individual do the DNS request to get that record is not and should not be public. That is your personal data. So that's a really clear idea to keep in your mind as we move forward. So having established the problem, we now start looking at solutions. And there were various ones that could have been looked at. Some of the well-known technologies, some DNS-specific solutions were offered as well, and drafts on all of these came forward to the working group at the time. The ones that got really serious consideration were these three. Start TLS initially seemed very attractive. It could be done on port 53. It could be incrementally deployed. It was a known technique. That was all nice. On the downside, though, obviously the negotiation can be susceptible to a downgrade attack. That negotiation can also introduce latency, an L word that DNS folks really don't like. And there was also a sort of big question mark about, hang on, there's all these routers that get DNS traffic on port 53. Are they suddenly going to freak out if they start seeing encrypted traffic and just block it? Are we going to have real deployment problems here? It was an unknown. So discussion moved on to looking at doing TLS or DTLS over a brand new port, if we could get one. Now, if we could, TLS is, a very well-known technology. There's a lot of implementations. It's quite widely deployed, so that was attractive. There were some concerns about scalability of it if you try and use it within the DNS. And then in some ways you might want to look at DTLS and say, well, isn't that a more natural solution for DNS because it's UDP based? And initially you might think that. However, it runs into the same problem that UDP does, and the reason there's this scattering of TCP around, which is that if the answer to a DNS query is too big to fit within the MTU, then the server has to indicate to the client it needs to retry over TCP because you can send that large response over TCP. The same problem happens over DTLS. If the response won't fit in the packet, the server cannot send the whole response and it has to request the client to retry over another mechanism. When you're dealing with privacy, that means if you want to maintain privacy, you have to use another protocol like TLS, or you have to completely sacrifice your privacy and retry over clear text. So the upshot of that was that DTLS couldn't be a standalone solution to DNS privacy. You had to do DNS over TLS regardless if you wanted a deployable solution. So in that case, it meant we had to revisit what's going on with DNS and TCP. I mean, some people are sort of shocked to find that TCP is even used for DNS at all. But it was, but not in such a great way. And the reason was a historical one. It was that clients took the easy route. And if they were doing lots of UDP queries and they got this signal to say, you need to retry over TCP, they would do one shot over TCP and then go straight back to UDP. And that was the pattern that clients implemented across the DNS. So on the server side, the servers were all sitting there going, well, I don't really have to worry about TCP. I'm going to get one query, every now and again. So servers had very basic TCP capabilities. Operators didn't routinely worry about tuning for TCP or robustness against TCP attacks. So, it was sort of in some ways at this point treated as a second-class protocol. Oh, sorry, I think I skipped ahead. In fact, I'm on completely the wrong slide. Okay, so we will have to go and deal with TCP over TLS implementations at a later point in time. Another problem that we will have to deal with is authentication. So what do most other protocols do when they want to authenticate something? They do a DNS lookup first. So we're going to have to get around that in the DNS. The other thing to worry about is some really interesting work that was done on traffic analysis. And what this showed was, great, go ahead and encrypt your DNS, that's fine. But if I'm an observer and I can see both sides are recursive, then I can see lots of messages, I can still figure out how big they are, and I can still see the timing correlations between them, which means with a bit of work, I can still deduce a whole bunch of stuff about what individual users are doing. So just encrypting the traffic is not enough to obfuscate that. So you need to consider options that can defeat that kind of traffic analysis. Okay, so top of that list was getting your port. How easy is that? Well, it turns out if you have a really solid use case, which this was, it's pretty easy. We asked and we got. Fantastic. So a year ago, port 853 was assigned for use for encrypted DNS. Hurrah. Next problem. Deal with this issue with DNS over TCP to enable DNS over TLS. So this wasn't an insurmountable problem. It was really just a question of engineering. So what do? Well, we throw the kitchen sink at it. Or, as Matt Damon might have said, we need to science the out of this. So what we do is you look at all the techniques that are used in all the other protocols that use these, and you make sure to introduce them into the DNS space in the standards. So for example, when DNS clients and servers are setting up connections, you need to make sure that they're using techniques like fast open, session resumption, and you want to have a really close eye on TLS 1.3 because that's going to do good things in terms of reducing latency for setting up these connections. When you set the connections up, you want to stop this behavior of one-shot TCP. You want to recommend that clients, once they have a connection open, they pipeline their queries over it, not waiting for responses, just send them, that when the server gets them, it actually processes them concurrently, not serially, and that when it gets the responses, it sends them as soon as it gets it. Now that all sounds really obvious, but that is not what DNS implementations have done historically. So work was done to ensure that in the standards, this was how implementations should mature moving forward. You'll also note there's a persistent connections RFC here. Until last year, there was no standard way for a DNS client and a DNS server to agree that they wanted to do persistent TCP. It just wasn't there in the spec. it is now. Also, in terms of managing TCP connections on a DNS server, then there's a huge amount that we can just learn from the HTTP world. These guys have been doing it for a long time, and not just HTTPS.
You have a typo. 7828. 7858 is DNS over TLS.
It is. Thank you. Yeah, keep alive is 28, isn't it? Thank you very much. Apologies. Oh, you're on fast. Okay.
Is this being broadcast?
It is. It's being YouTubed. Yes. Yeah. Sorry. So there's a correction to the RFC number for persistent connections. It should be 7828. Thank you, Stuart Cheshire. Okay. And this was just a little illustration of sort of bad DNS over TCP versus good DNS over TCP, which is where we want to be. Okay, so having done some work on that, we now move on to authentication. The work that's going through DPRIVE at the moment has attempted to present two profiles in order to clarify to users what security they can expect when they use one of these two profiles, because this is kind of a new idea to DNS users. So at the moment, what's specified are two profiles, strict and opportunistic. So the strict profile is one where, as a client, you decide that if I'm going to do DNS, I want to get an encrypted connection and I want to authenticate my server. And if I can't do both those things, then I am not prepared to compromise my privacy, so I just won't do DNS resolution and I can't get to the internet. But that is somebody saying my privacy is more important than my connectivity. And that's a choice to make as a user. So it's kind of a purist take on it, if you like. I like to think of it as a kind of Jedi way of doing this. I've let the words of Master Yoda describe the philosophy here. Whereas the opportunistic profile is much more pragmatic. I really like the idea of DNS privacy and I think it's important. I'm going to try every mechanism I can to do it. But at the end of the day, I am willing to go to clear text in order to get connectivity. And again, that's just a usage profile for users to make depending on what they consider important in terms of exposing their DNS queries when they use the internet. So hopefully this is something where opportunistic is a stepping stone to everybody being enabled to do strict, and it's not an issue. But that's something for us to determine as we roll this out. So how do you do this authentication? Well, right now there are two ways specified. One that starts off from a domain name and one that starts off from an SPKI pin set. Now, if you're out there, you're thinking, okay, these are the DNS folks, and aren't these the folks that tell every other protocol, if you want to do authentication, you should be using DANE. So shouldn't we be kind of eating our own dog food here? Well, yes. So we do specify how to do authentication via DANE. But a really interesting idea came out of the work on this because you've got DNS servers involved in this interaction. So this is a very quick demonstration of how it would work using kind of classical DANE. So you start from a DNS client that has DNSSEC validating capabilities. You configure it with a domain name and an IP address, and one of the bootstrapping problems here is that it may need to do opportunistic, so not necessarily encrypted lookups to get that information to start with. Again, at this point, I don't have a connection to a privacy server. So if I want to get those DANE records, that also has to be opportunistic. So probably it'll be encrypted but not authenticated. But I need to go off and talk to some resolver and get those records. Once I have those records, I can use DNSSEC to validate them, say I'm good to go. Then the client can start the TLS connection, get the credentials from the server, validate them, and DNS resolution can start. The alternative mechanism is one using something called the TLS DNSSEC chain extension. And this is a draft which is currently going through the TLS working group. What this does is it starts from exactly the same point, but it shifts the responsibility for getting those DANE records onto the DNS privacy server, because after all, it's a DNS server. It should know how to get them. And it can prefetch them and it can cache them, or it can get them on demand. In this case, once that server has the records, the client can then, in the client hello, indicate that it supports this new extension, the TLS DNSSEC extension. So, hey server, I know all about this new extension. Do you? Yes, I do. Here, have my DANE records in the server hello, along with my credentials. Have at them. The client goes, fine, lovely. Okay, first up, I'm going to validate your DANE records with DNSSEC because I'm a validating client. I can do that. Next up, I validate your credentials against them, and off we go. DNS resolution begins. But of course, the beauty of this is that all that happened inside the TLS handshake in this case. So what you avoid is the latency of those separate lookups by the client, and you also remove the need for a separate resolver that can provide the DANE records. So this streamlines the whole process. Okay. So on this slide, I'm just presenting where dPrive is today in terms of the documents it has in the solution space for the stub to recursive part of the problem. So in May of this year, 78-58, got it right there, was published, which is a specification for DNS over TLS. Alongside that, 78-30 was published, which is the eDNS zero mechanism so that you can pad a DNS query by an amount. There's more follow-up work to talk there about what algorithms to use to pad that, but at least we have the basic mechanism in place. There's also a draft going through the working group, which has completed working group last call, to specify DNS over TLS. And there's a separate draft, which is in working group last call, to specify all the details of the authentication mechanisms that I touched on earlier. So this is pretty good work for 2 years of a working group. I think hats off. You know, this wasn't an easy problem, and a lot of progress has been made. So what next? Now we have to start biting the bullet and thinking about the recursive to authoritative problem. And in fact, the working group is meeting this Friday here in Seoul, and one of the agenda items is the recharter discussion. How do we move forward from where we are to tackle this? There is a draft available, and what that attempts to do is enumerate 6 options for how to do that authentication between the recursives and the authoritatives, and that's also going to be discussed in the working group. There's also quite a desire to get some data from the experience of what it really means to do DNS over TLS on stub to recursive and feed that into information about how to do that recursive to authoritative as well, because this is new territory. One thing I do want to touch on is that, okay, we don't have an encryption solution for recursive to authoritative yet, but what came out of the DNS op working group is a nice piece of work, you know, minimization. So we go back to this picture earlier where the bad idea fairy said, leak all your information. And we come along with an idea from the better idea fairy who says, well, no, don't do that. Just send what you need to and stop leaking information. Now, this looks totally trivial, and it's not quite. There's some really icky corner cases in this when you have to go following CNAMEs and the like. But the good news is those are being solved in implementations, and this is now being rolled out in some of the major open source name server implementations today. So I've got this slide up here, and this is to do with the data handling. And honestly, I think this is the area that has had the least attention and probably has the least progress and needs to be somewhere we're focusing now. I mean, so I could start by saying, hands up, who in this room has read the small print of their ISP contract and knows exactly what their ISP does with their DNS data? And I'm not one of them. So, wow, you all have lives. That's great. So that's a thing. And we're the kind of people who should really know and care about that. So what we need to be doing here is looking at more that needs to be done. So, for example, government policy and practice in terms of surveillance and data sharing, particularly in light of some recent political events. We might all want to be thinking about this. Had to say it. Also, what you really want is much more transparency from users and providers about what are they doing with their data? Why is it in small print? Why isn't it upfront and easy for you to find out? Similarly, okay, if you have to keep data, do everything you can to de-identify it. You can still do a lot with the data, but in terms of certainly academic exercises where you try and collect data, day in the life of the internet and the like, there needs to be thought given to de-identifying that data to protect users. A very quick note on a couple of topics here. So DNS over HTTPS has actually been around for a while, non-standard, but used. There's a really good review of why it was used. And some of the motivations, well, one was privacy, it brings that with it. Others were bypassing middle box interference. Others were exposing higher level APIs. But this is kind of gathering a bit of momentum. So it's not actually being positioned as a privacy solution first and foremost. It's much more a new technology, and there are drafts to specify how to do this. Google is actually offering a DNS over HTTPS service using a sort of non-standard implementation. But there's actually now a non-working group mailing list, and there's going to be a BOF on Tuesday night on this topic. So if you're interested in this side of things, I'd encourage you to go. So this is the matrix that I showed earlier, where what we're trying to show is the current mitigations that we have for those hotspots. So recursive stub to recursive, we have encryption and authentication. Today, for recursive to authoritative, we have the mitigation of QNA minimization, and we're working on the encryption. And it just recognizes that the area of data policies is something we really need to be working on. And also to mention that there is a draft to solve the DNSSD problem. That's been adopted by the working group, so there's progress in that area as well. So to quickly move on to implementation status. So I just want to show these very briefly, just to show that there is activity in the uptake of the new standards within DNS. So these are 3 well-known open source DNS name servers. Other implementations are available, I should stress. I've just chosen 3 to illustrate it. But there's work in all of these on the new standards that are happening. The purple box in front of bind is there because at the moment, the approach of the bind folks is not to put TLS directly into the name server. Rather, what they're proposing is using a TLS proxy in front of a name server. And there are lots of technical reasons this makes sense, and there are lots of ones available. So this is certainly a viable way to do it. On the stub side, most of the energy and effort has been expended over the last few years towards GetDNS, and I'll talk about that a little more on the next slide. You'll notice some notable emissions from this in terms of deployed and used libraries, and that's a real challenge in terms of getting new features into those libraries. So essentially, there's uptake of this, there's implementations of DNS over TLS. We're waiting for an implementation of DNS over TLS. That would be good to add to the mix. And BII has a DNS over HTTP implementation that's available as well. So to talk about what's deployed and what's actually out there, there are a handful of test servers available today that are up and running to start on getting operational experience at how you do DNS over TLS. So NLNet Labs are running one, OARC are running one. There's a few hosted by SurfNet. DKG, the man, has put one up there. And so these are there to start doing activities. There's a question mark against IETF because we sort of started exploratory talks about, well, maybe the next IETF could offer a privacy server, maybe this one even. I'm getting faces from Warren, I won't ask that. But that would be a nice step just to offer that so people can get experience. If you want to know the details of these servers, they're at a webpage under that link. So in order to use those servers, you need some client software that will connect to them. And what has been being developed over the last few years is based around GetDNS. So if you're not familiar with it, GetDNS is a modern asynchronous DNS SEC-enabled API. Bunch of information at the website. What it does do is it already implements DNS over TLS, and it is already a natively validating DNSSEC client stub. So it ticks 2 boxes in terms of enabling privacy. So what has recently been developed in the last release is a new mode of using GetDNS, which is called Stubby. This is the mascot for it, Sergeant Stubby. I'll let you Google him if you're interested. But basically what Stubby does is it runs as a daemon on your machine. You point your OS DNS resolution to localhost. Stubby listens on localhost, picks up your queries, and sends them out of the internet over TLS, protecting your privacy. You can configure it via a configuration file. In that file, you can set up all the name servers that you need. You can specify the authentication information you might want to use. You can specify which of those two profiles do you want to do strict or opportunistic. This is all configurable. There's a web page on how to build Stubby, configure it, and use it. And if anybody's interested in actually getting hands-on with this, then come and find me or Willem Turrup or Alison Mankin, who are busy hacking at the moment in the hackathon. But any of us would be happy to give you a tour of this. So that's a simple configuration file, and if you really care, you can set it up to do minimal logging, and you can actually watch it as it feeds your DNS queries out over TLS connections and see the behavior of those upstreams as it answers your queries. So just to mention what's still ongoing at the moment. As I mentioned, there's been a lot of work in the hackathon this weekend. We're doing a lot of interop testing between Stubby and some of these upstream servers. So we're hopefully maturing this and making it much more usable. A challenge that I haven't really touched on much is that of integrating not only Stubby, but other client solutions into OSs, making them accessible, making them usable for users. And this faces a very similar challenge to DNSSEC in that respect. So hopefully we can learn something from that. We need more completeness in the recursive implementations, more deployment, and obviously there's still the recursive to authoritative work to tackle. So to summarize, I hope I've convinced you that DNS privacy is a real problem, and it's a relevant problem as well, one we need to be thinking about and working on. That there is active work, but this is a large solution space. There isn't going to be an overnight solution, but that work is in progress. And that there are test implementations out there that you can use today if you're interested, and there are more privacy services and more solutions on the way. Also, I think in the very near future, the public awareness of this is going to continue increasing. After all, Edward Snowden got Hollywood film out of this, so people are aware of the problem and are thinking about it. And I do have hopes that one day there might be an IETF, the movie, to recognize all the folks here, all the operators and all the implementers fighting the good fight to defeat pervasive monitoring, and that will happen one day. And casting suggestions for that movie will be very gratefully received in the bar later on. So with that, I will thank you for your time. I will point you at a SurveyMonkey website, as I have been instructed to by the EDU team. If you can give feedback on this, that would be great. And thank you very much. I'd be happy to take any questions.
Lorenzo Colletti, sadly not DNS specific. So for as long as SNI exists, this is all in vain, right?
Yep.
So DKG, take it away. Tell us how you're going to fix that.
You came in late. So
leaky boat?
You missed.
I heard leaky boat.
You saw the leaky boat. Okay.
Yeah. So how do you fix the other leak?
So that's not something that we can fix in the DNS. There are a couple of possibilities. I tried to get that into TLS 1.3, and I got pushback from some large server operators that didn't want to incur an extra round trip, which is understandable. So it's not going to be automatic in TLS 1.3 at any rate. So there's a couple of possibilities that would allow SNI cover traffic, basically. And I'm not going to go into that right now because I think there's other people with questions about the DNS, but I'm happy to talk with you afterwards. And if anyone has other specific ideas about DNS, TLS SNI, I'd love to hear them. Also, this is not just for TLS. So, right.
Jim Reed, I just happened to have wandered in off the street. Sarah, I want to introduce a layer 9 question here. Have you had any conversations with any of the data protection authorities about whether this DNS query traffic would be considered as personal data or not?
not direct ones, and also that's going to vary country by country. I mean, that's a huge issue, and I'm not sure it's necessarily for us protocol folks to try and tackle. I think that goes up a level to an organizational question. What has been remarked is that it will be quite interesting if these there's uptake in terms of this test servers, and it's observed that DNS traffic is being routinely encrypted, and how certain monitoring authorities might react to that in terms of exact obfuscation of personal data. I don't know, that's an unanswered question.
I'm just thinking this might be a way to help with uptake of these technologies once they become more widely accepted and widely deployed. And there's also, as you're probably aware, is a lot of operators, particularly in the European Union, are very concerned about data retention and all those other considerations. Yep. So stuff like DNS query traffic is already an issue for them. So if there are ways in which that problem can be minimized from their point of view by using some of these obfuscation technologies, yep, that could also be a good thing. But the message would then have to be coming from things like the data protection authorities that says, we consider this personal data, you need to start taking things much more seriously about how you treat and handle that data.
Yeah, and I agree. I think that's an area that hasn't received as much attention as it should have, and certainly will need to in future. Thank you. Any other questions? Nope. Okay. Thank you very much again. I think that's a wrap, everybody. Thank you.
Come to the DeepRive working group on Friday.
Yes, come to DeepRive and help us figure out what to do next.
I think the HTTP, the DNS over HTTP BOF is, I think, Tuesday.
Tuesday.
Ask him what time zone it's in next.
He said Tuesday. I don't know which Tuesday. Thank you for the. Thank you for the.
On the UDP anonymity profile. Apparently, sort of people said things are now like we're considering whether to delete the host name entirely in the DHCP request or replace it with junk. That's one thing. Right. So